Okay, we're now at the stage where we have a pretty clean audio novelty function which correlates with rhythmic events. And we should definitely test it more on more than just one tune, and we will do that. And we'll see other improvements that we can make on this in the next assignment. But for now, this is good enough. And we can start to make some observations about this and extract more information from it. So I'm going to use this as the base representation for the next set of things I want to do. And the first thing I want to do is tempo estimation. So estimating, well, how many beats are there per minute? So if I keep time. And actually I find with this tune, there should be 83 beats per minute. That's what the internet told me for Come Together by the Beatles. And this is, something that we have to assume is fairly constant in the region we're looking at. And this is pretty typical in popular music, is that you're not going to speed up or slow down the tempo by a ton, at least not locally. What that leads to is this periodic pattern in the audio novelty function, because the beats occur at regular intervals. Now, you're not going to have a beat for every single interval. Sometimes there'd be syncopation and other effects like that. Sometimes there'd be pauses in the music. But generally, you're going to see this periodic thing. And if we figure out what the period is, so what is the spacing between the peaks, between the beats, we can estimate the tempo. So that's what we're going to learn how to do now. Okay, the tool we're going to use to estimate tempo by looking for periods in this audio novelty function is a tool called autocorrelation. And we've actually seen this before in the context of convolution and its Fourier transform. So we defined something before called the autocorrelation, which was the convolution of a signal in its reverse. And we saw that you could exploit these interesting properties of the Fourier transform that you could show that the Fourier transform of that was actually the magnitude squared of the Fourier transform of the original signal. But I want to present this in a slightly more intuitive way, and one that is going to help us to understand how we can use it to estimate tempo. So let me define autocorrelation a slightly different way from the convolution of a signal in its reverse. So given a signal xn with n samples, the autocorrelation Rk is defined as the following. So we say Rk is the sum from n equals 0 to n minus 1 of x of n multiplied by x of n minus k. All right. So this is saying what you really are doing for a particular k, you're shifting the signal to the right by an amount of k samples, and you're taking the dot product. So the sum of these products. And what that gives you is something pretty interesting. So what I'm going to do is I'm going to show you shifting this signal, and then I'll show you what the dot products are, and that's the autocorrelation. We'll see what happens as we shift it. So orange is the shifted version. And I notice that when it lines up, when I've shifted by an amount equal to some whole number times the period, I see that the periods line up and I get a peak in the dot product. So let me start that over again. So at the beginning here, it correlates with itself a lot, okay? So that's just the dot product of the signal with itself. You start off with a large value, but then you decrease. But then as soon as the periods line up, you peak. And then they line up again, you peak. And then they line up again, you peak. So that's what the autocorrelation is actually doing. So let me go back and compute this directly from the definition. So I will say def autocore, and I'm going to call autocore slow because this is not the best way to do it. But I'll take in a signal x. I'll record the length of x. And let me just follow this definition directly. So I'll say r is equal to np times 0 is n, 4k in range n. I'm going to have some accumulator variable, which is going to store the sum of products. Now I'll say 4n in range n. If n minus k is greater than or equal to 0, then I can say core plus equals xn times xn minus k. Good. And so once it's gone through this full loop, I can save it away. I can say r at index k is equal to core, and return r. All right. So let's just plot what that is. plt.plot autocore slow of the novelty function. And yeah, this is the pattern that we got. If we remember, go back to the animation. That lines up pretty well. That looks exactly the same. But this is not the most efficient way to compute it, though, with the nested loop. Those of you who have me in algorithms would say that this is an n squared algorithm. So it's quadratic time complexity algorithm. For each k, you have to loop through n elements, and there are n k, so that's n squared. But we can do better. We can come up with an n log n algorithm by using that thing I taught you before, which is the fact that the autocorrelation of a signal is the convolution of that signal and its reverse. So let me define a more efficient version by saying what I'll do is take this in. I'm going to take the Fourier transform, but I better actually take the Fourier transform of a zero padded version, because I notice that's actually what I'm shifting here. When I go beyond the signal extent, I don't want to include that, but I want to make sure it doesn't loop around, because the Fourier transform assumes that it's periodic. Okay, so I need to zero pad to make space for this all to happen. So I'll say x pad equals, so I'll say n is equal to length of x. X pad is equal to np.zeros n times 2, so I'll zero pad it by twice its extent, so I have enough room to shift it by its full amount. Then I'll say x pad from 0 to n is x, and the rest are zeros. Now I'll take the Fourier transform of x pad, because I'm going to use the fact that the convolution of two signals in the Fourier domain is the multiplication, so I can use the Fourier transform to efficiently compute the convolution. Now actually, do I need to then also compute the Fourier transform of the reverse of the signal? Turns out I don't, because it's related to the Fourier transform of the original signal by just the complex conjugate. So what I know actually is that the Fourier transform of both is going to be equal to the Fourier transform times its complex conjugate. And that turns out to be just the real component of f squared plus the imaginary component of f squared. So this is the Fourier transform of the convolution of x and its reverse. Cool. So I told you that the convolution of the signal and its reverse is the autocorrelation, so now I've got the Fourier transform of that. I just need to go back. So let me return mp.fft.ifft, let me do the inverse Fourier transform and get us back. Okay. And actually, let me only take, since I've zero padded, I'll just take the first n samples here. So this should give me, even though it looks really different, it should give me the same answer as this. So let's just check it. So I'll say plt.plot autocore of nav fn. And look at that. Gives me the same answer. Actually, just to really check, let me compute the difference between the two, and we'll look. So this autocorrelation fast minus the autocorrelation slow, what does that give me? Okay, they're a little bit different. Oh, but this is just numerical differences. So this is on the order of like 40, 50. But look, this goes up to 10 to the 10th, so that's nothing. If I take the ratio of the difference to one of them, I'll see that this is like negligible. So let me, if I compute that, okay, so I see this is 1 times 10 to the negative 8th difference. All right, so this is looking pretty good. So I've got my fast version of the autocorrelation. Now that I know I can compute it quickly, let me examine it a little bit more. So let me save this away into a variable. And let me look at it. So what I notice is there are these peaks that happen, right? Every time a signal lines up with itself. Well, signal lines up with itself as I shift it in intervals of its period. So let me examine the times of the shifts and plot those. So the times is np dot a range length of r times the hop length over the sample rate. So if I look at, oh, and it's complaining casting complex to real. Let me just, there's some numerical stuff that's causing negligible complex numbers to come along with this. Okay. So if I look at the peaks of this, the peaks occur when the signal lines up with itself pretty well. Let me just look at everything that's above, we'll say 0.8 times 10 to the 10th. So let me print out the times where the autocorrelation is greater than 0.8 times 10 to the 10th. That's what we saw here. Now it's probably helpful actually if to understand these we plot a line that shows the cutoff that I'm taking. So 0.8 times 10 to the 10th. Alright, so it's that cutoff there. So everything above there we're going to take. And when we look at the times of the shifts corresponding to these peaks, they're as follows. Now, I was given the tempo of this tune in beats per minute. So it was supposed to be 83 beats per minute, and that's the way that it's normally counted. Same way a heartbeat's counted too. So let's convert that to beats per minute. So I'll say intervals equals that. So what we notice is, okay, intervals come out, that's the period of the beat. We convert period to frequency as 1 over the period. But that would be the frequency in terms of beats per second. So then we need to multiply that by 60. So actually we say beats per minute is equal to 60 divided by these intervals. So let's print that out. Whoops, gotta do that. Okay. Now it's complaining to me because one of the times that I get is 0. So one of the peaks occurs right at the beginning when the signal is fully lined up with itself with no shift. So 60 over 0 is infinity. It doesn't like that. And then there's also, you know, there's a sample rate beyond that also makes it past the threshold, like a really small shift that you would mistakenly think this is a very high frequency. Okay. But if I look through this list, okay, I see a few things that are kind of close to each other. Let me take the one at the center. So that's 161 beats per minute. Same thing here. Now here's where I see actually the correct answer show up, 83 beats per minute. Right, that was what we got. So we're getting it somewhere in here, but we're also getting twice that. So if you listen to the clip, it's actually been subdivided. So 83 beats per minute is, but actually it's been subdivided, so it's 1 and 2 and 3 and 4 and. So you're hearing those, you're actually, it's picking up on the subdivision. That's why we end up thinking that it could possibly be twice that, 161 beats per minute, because it is periodic in that way. Also, we get half that. So 83 beats per minute, we also get 41. Because if it's periodic at 83, it's also periodic at 41. That's like saying, you know, I repeat myself 83 beats per minute, but actually every 2 beats I also repeat myself. That would be true. So that's the reason. So the autocorrelation itself is actually periodic. And it's not always clear which peak to pick, which corresponds to the true tempo. And not even human annotators would agree on that. So, you know, we're going to look at some tricks to try to figure out what the max peak would actually be. In a quick exercise, I'm just going to have you pick the max peak beyond like index 2, because we know that the first couple are probably just run off from the signal lining up with itself. And that's sort of a first approximation, but there are better things you can do. So in this case, I would pick out this peak here, which would actually correspond to twice the tempo. That's pretty good, though. I mean, that's, you know, it's kind of neat that you can actually realize that you're at least finding the microbeat, so the 1 and 2 end. So you totally nailed that doing this technique. So it's a good first pass. All right. So I'm having you do a quick exercise, and then there's one more thing I want to talk about before class.